So we stopped here yesterday, in the last class, we stopped here. Current series feedback amplifier. We also discussed the other type, that is voltage shunt, right? We have discussed the voltage shunt feedback amplifier and the current series feedback amplifier. Still, two types are left. What are those? Voltage series and current shunt. Right. We have discussed the block diagram representation of all these four types of feedback amplifiers: current series, voltage shunt, and current shunt. But as far as the BJT based implementation is concerned, we have only discussed the current series feedback amplifier and the voltage shunt. And last day I have told you that this voltage series and current shunt, fortunately and unfortunately, both, this voltage series and current shunt cannot be designed using a single stage common emitter amplifier. Either you can multi-stage or you have to go for some other types of amplifier, not the common emitter type, either common base type or common collector type. Now the thing is that you have already identified that this feedback is represented by the sampling mixing topology. Sampling followed by mixing. First sampling, then mixing. Now we have already discussed voltage shunt. We have already discussed voltage shunt. We have discussed voltage shunt. We have also discussed the current series kind of amplifier, feedback amplifier. What you need to do is that you have to develop, say for example, I'll start with, say let it be voltage series or current shunt, whatever it may be. So you know that for sampling, we have identified voltage sampling as well as current sampling. We have already identified how to take this, how to gather this signal. Similarly, how to feed it. Series, shunt, both we have discussed. So we have discussed this part, how to sample voltage. We have discussed how to sample current. We have learned how to mix in shunt path, how to mix as a current, and how to mix it in series path. That means how to mix as a voltage. So what is left? Left is this voltage series and current shunt. But unfortunately, that cannot be designed using single stage. So there is a very, primitive question in the semester examination, that why voltage series and current shunt? Because if I ask you the questions like, okay, you just draw the feedback amplifier which exhibits a voltage series kind of feedback or current shunt kind of feedback, and find out the expression for the voltage gain with feedback factor, you'll be able to draw and explain all these things. Now the tricky question is that sometimes it is asked that why this voltage series? You know that voltage series and current shunt cannot be designed using single stage common emitter amplifier. For the time being, let's focus our discussion on common emitter amplifier only, and gradually we will move to common base and common collector. So it is not possible to design the voltage series and current shunt using single stage common emitter amplifier. That is the question. And once you understand this question, once you understand the problem, then you will be able to have the two-stage or multi-stage kind of representation.
Voltage series can I use for that?
No, you have to design voltage series, but not using a single stage. Let's focus our discussion only on common emitter. But the question is that why it is not possible? Why it is not possible to have a voltage series kind of thing? For example, voltage series kind of thing. So let's identify voltage series only. So it is not possible to have a voltage series kind of thing, voltage series kind of feedback amplifier using single stage common emitter.
Output comes the
Because you know that voltage, you know the voltage sampling, current sampling. You already know the currents, shunt mixing and series mixing. So basically mix and match kind of thing. I don't know how many of you have heard of Sukum, the name of Sukumar Ray. How many of you in this particular class? Only very few. Name? Have heard, no? He is known to be the pioneer of nonsense Bengali poem, right? Nonsense. If you have heard of this one, yes, if you have heard of this one, the combination of Hans and Hojadu, that becomes Hansjadu. The combination of Bok and Kocho, that becomes Bokacho. Something like that. So if you have voltage shunt, if you have current series, you combine them, they will become voltage series and current shunt. Something like that. You take the voltage out of voltage shunt, you take the series out of current series, match them, it becomes voltage series. Look something like that. It's not that easy. Why not? Okay. So for common emitter amplifier, if I would like to have a voltage kind of sampling, what do I need to do? Typically,
voltage kind of
voltage sampling. For common emitter amplifier, voltage sampling. That means what? I have to take the
output
yeah. So I have to take the output from the. I have to take the output voltage. In parallel path. I have to connect. I have to connect this output side of your feed network to the input of the back network in such a way that this voltage is retrieved. So voltage is retrieved in which path? In parallel path, in shunt path. Right? So I can design, I can have this kind of thing. As you know, so VCC there, RC. So this is the voltage, right? V out. Let's assume some biasing is there already, some biasing is present. Right? So I have to connect this one, this output voltage. I have to gather this output voltage so that it becomes a voltage kind of sampling. How to mix? How to mix? It's a voltage series. How to mix? Series mixing. Series mixing means what? You have already observed for this one for current series kind of feedback. Right. So whenever you are considering some series kind of mixing, that means you should have a resistance present over there and you connect like that. So for example, it might be something like this, might be. You have a resistance, right? And if I connect this voltage over here, it becomes a shunt kind of mixing. But what I want a series kind of mixing, right? So I have to create some series kind of mixing. So what you feel that okay, might be something like that. Let's have some different color. Might be something like this. Might with some resistance, for example. Suppose there is some resistance between this and that. But the question is that, so what is on an assumption? Okay, suppose it is possible. Let's assume, as I told you, the combination of Hans and Hojadu will become Hansjadu. Something like that. You already know how to design a voltage shunt kind of thing. You already know how to design a current series kind of thing. So let's have the voltage out of voltage shunt and let's have the series out of current series and let's combine them together. So I can do that. So what I'm saying, suppose this part is not there. It's something like this. Suppose I connect some resistance and put over there. So the question is that, does it solve my purpose? Is it a feedback? What do you feel? For a common emitter amplifier, what happens for a common emitter amplifier? As you understand, if the input signal goes like this, output is a magnified version and there is a phase reversal, right? Is it okay? If the input variation is something like that, then the output variation is something like this. So therefore, when you have some positive change of the input, you have a negative change in the output. And remember, this back network consists of only the resistances. In the feedback amplifier section, we will understand that this beta network or B network that we have discussed last day, the back network, it is composed of only the resistances. No other frequency selective elements, only resistances. And as you understand that the resistance is a particular element which is not frequency sensitive. So therefore it will only obey the Ohm's law. Right? So therefore, from here to here, there is no feedback. I mean, there is no phase difference because you have a resistance only. Right? So whenever it goes positive, this goes negative. So the signal that is being fed back at this particular point, at this emitter terminal over here, it is also having a negative kind of fluctuation. Right? Now this is applied at the emitter terminal. But you find the base potential is increasing. On the other hand, the emitter potential is reducing. So what is the base emitter drop? That drop gets increased. That particular drop gets increased. Right? So you don't really experience yes, it's a feedback, but you don't really experience a negative kind of feedback. Because whenever this voltage goes positive, this input voltage, this output voltage goes negative, and the portion of this is fed back over here. So this voltage is also having this negative kind of thing over here. So this base emitter drop increases. So it gives rise to a kind of positive feedback that you don't want. So what is the way out? What is the way out? I can show you the complicated circuit at the very beginning and tell you to analyze the circuit. But before doing that, let's try to visualize why this is so, what is the problem, what is the bottleneck, and then accordingly you design your own circuit. Can you get my point? You know that how to sample the voltage. You have to connect something in parallel. You know how to feed it in the series path. You have to connect it in the emitter terminal, and there should be an emitter resistance. So that this voltage, so that means what you are doing whenever you are using this current series kind of thing in the last day, that means you are basically breaking the loop. Series addition means you are breaking the loop. So that loop was there over here, that loop was there, and you have the loop and you have connected this particular thing. Right? So there is nothing wrong over here. There is nothing wrong over here as well. But still the problem is that you cannot directly connect over here. The problem lies in the fact that this voltage and this voltage, input voltage and this voltage, they are out of phase. That is the problem. Can you get the point? So obviously you have to take the output like this only. You have to sample the output like this. You have to fit in series path like this. There's nothing wrong. This and this, they're out of phase. Common mode amplifier, single stage, out of phase. So nothing wrong in connecting like this. Nothing wrong in connecting like this. But remember, these two are out of phase. This and this, they are out of phase. So by some means, if this voltage and this voltage, they are in same phase. If they are in same phase, then whenever it goes positive, this is also positive, and portion of this is also positive. That gets subtracted from this positive. So we have the feeling of a negative feedback. So how to ensure that? When this goes positive, this also goes positive. No phase reversal. How to ensure? Yes, so you need another kind of another stage of such amplification, two-stage amplification. So that 180 phase shift after one stage and another 180 phase shift at the second stage. So that it becomes 360 degree. That means 0 degree phase shift. Now if you take this output from this particular terminal, so this and this they will be same phase, and from here to here same phase because it's the resistance. And if this goes positive, this also goes positive. So this difference can be reduced. That is explanation. Now with this basic understanding, let's move to the voltage shunt we have discussed already in the last class. Yes. So with this understanding, let's move to the voltage series feedback amplifier. Let me just show you the amplifier circuit first, and then we will move into the small signal model. So this is the first stage of amplification, right? What you have? You have these two resistances R1 and R2 for providing voltage division bias. This resistance RC1, collector resistance. This emitter resistance RE1. And after this coupling capacitor, you have this. This is the voltage, output voltage VO1, and after coupling capacitor, this voltage gets coupled at the input of the second stage. In the second stage, it's basically the replica of the first stage. You have another R3, R4 combination for biasing. Remember these two stages, this stage 1 and stage 2, they can be biased separately. So that's why this capacitor is present. They can be biased separately. So that's why you look at R1, R2 here, you have R3, R4 there. Right? You have RC2 present over there, output resistance for the stage 2. And for this particular stage, second stage, you don't want to have some local feedback. Because as you know, you have already studied that for current series kind of thing, if I have some unbypassed emitter resistance, that gives rise to current series kind of feedback. If you can remember this one, current series, this one, unbypassed emitter resistance, right? So that's why you don't want to have some current series kind of feedback whenever we are going to design some voltage series kind of feedback. So therefore, this particular emitter resistance is bypassed by means of some bypass capacitor. Okay? So therefore, there is no such local feedback present over there. Right? Then you understand that, okay, this part, so if my input variation is something like that, over here, there you can expect like this, phase reversal, 180 degree, and then another phase reversal. Same phase. So here so if it is 1, if it is 2, and if it is 3, so between 1 and 2, you have 180 degree phase difference. Between 2 and 3, you have another 180 degree phase difference. So between 1 and 3, you have 0 degree phase difference. Okay? And then what you are doing, you are feeding this voltage. You have not broken the loop because it's a voltage sampling. Feeding it back through a resistance RF, where? At base or at emitter? At emitter, because it's a series feedback. So back over here, right? So notionally, it seems that it's a voltage series kind of feedback amplifier, and then we need to prove that really it's a voltage series kind of feedback amplifier if it follows that particular configuration, this block diagram model. Okay. But typically we use voltage divider bias. But this bias doesn't have any significance while you go for the small signal analysis. Right? Doesn't matter. Typically we use voltage divider bias in most of the cases, right? Now try to identify each and every element of the small signal model. Each and every element. Try to understand. First of all, this combination, this thing stands for the first BJT, right? R pi 1, GM1, V pi 1, and RO1, first BJT, right? Clear? This is the base terminal. From base to ground, you have R1 R2 parallel combination. Because this is also AC ground, this one. So you have R1 R2 parallel combination between base 1, B1 to AC ground. Okay. This voltage between base 1 and the emitter 1 is basically the V pi 1, the voltage across R pi 1. That is the V pi 1, plus minus. This side positive, this side negative. Okay. You have GM1 V pi 1, voltage dependent current source between collector and emitter terminal of BJT1, and you have this RO1 connected between C1 and E1, collector 1 and emitter 1. Done. Similarly, you have this one, R pi 2, GM2 V pi 2, RO2, this one for the second BJT. R pi 2 is connected between V2 and E2 with this side positive, this side negative. This is the V pi 2 voltage. GM2 V pi 2 is the voltage dependent current source between C2 and E2, and RO2 is connected between C2 and E2. Right? And for this voltage, for this particular stage, second stage, you have this R3 R4 parallel combination which is present between collector, between the base terminal and the ground terminal. Base and the ground terminal. Now here, what I understand, this RE2 is, since the RE2 is present and we have a coupling, we have a bypass capacitor present over there between this emitter 2 and the ground. But the mid-band range, what I can expect, that this small signal is basically grounded through this particular bypass capacitor. So effectively, under small signal operation, this emitter 2 is at AC ground. Because the reactance provided by this particular capacitor, bypass capacitor, is small enough as compared to RE2, so that this RE2 CE2 parallel combination will give you a zero reactance, zero impedance. So that means this is equal to, this point is held at AC ground. Right? Is it okay? So for the time being, let's assume that this R3 R4 is there between base 2 and some potential. Suppose this potential, some potential is there, for example. What else? You have another resistance here, RC1 between collector 1 and AC ground. RC1, collector 1 and AC ground. So this RC1 is connected between this collector 1 and AC ground. What about the collector 1 and base 2, C1 and B2? DC wise they are at defined potential because you have a capacitor present over there. So DC wise they are at defined potential, but as far as the small signal is concerned, if I assume that this reactance provided by this capacitor is small enough so that this is basically shorted. So therefore, previously what I understand that this R3 R4 parallel combination was there between B2 and AC ground, and RC1 is there between C1 and AC ground. And since we have identified that C1 and B2 they are at the same potential AC wise, small signal wise, so I can have this C1 and B2, I can have a short circuit connection. Okay, and therefore this RC1 and R3 parallel R4, these two resistances, they are in parallel. Where are they connected? They should be connected to, one terminal should be at C1 or B2 and the other terminal should be connected at ground, AC ground. But here it is what? Here it is E2. Because you know that E2 is essentially at AC ground, as I already mentioned. So therefore I can safely connect this RC1, R3 parallel R4 and R pi 2, all of them between this C1 or B2 and AC ground. Is it okay, this part? Any doubt? Anybody having any doubt of this part? What else? I have only two elements still left to be discussed. One is this RE1 and second one is this RF. How is RE1 connected? RE1 is connected between the emitter 1 terminal and AC ground. So this is your emitter 1 terminal, this is emitter 1 terminal, right? So this is your RE1, this is the ground line, for example, this is the ground line. right? So RE1 is connected between emitter 1 and AC ground. What about RF? This resistance, this feedback resistance, this is connected between collector 2 and emitter 2. Sorry, emitter 1, collector 2 and emitter 1, C2 and E1. So this is your C2 terminal, collector 2 terminal. So from C2 to E1, this is emitter 1 terminal. So between E1 and C2, you have this RF connected. Okay. Then, as you understand, this is your ground line. This is the ground line, right? This is the ground line, and this emitter 2 is also at AC ground, right? So these 2 points has to be connected. It should be short circuited, right? Okay, that completes the entire small signal model. Now you have to identify how this particular configuration develops some feedback. So you have to identify which is my feed network and which is my back network. First of all, you have to identify how can you sample this signal at the output of the feed network. How is it sampled? How does it look like? Is it a voltage sampling or current sampling? Voltage, because these are the 2 nodes. These are the, if I consider these are the 2 nodes, these which has been shown by green, output of the feed network, and this violet green combination, these are nothing but the input of the back network. How are they connected? They are connected in parallel path. So this is basically a voltage kind of sampling, right? And then if you move to the output of the back network, or which has been fed to the input of the feed network, how is it fed back? How is it fed back? The loop? You have broken the loop. So this is a kind of series mixing. So voltage sampling and series mixing. So it is known to be a voltage series amplifier. Right? So voltage series feedback amplifier using multi-stage common emitter amplifier. I have already explained why it is not possible to have a single stage common emitter amplifier to develop a voltage series kind of feedback. Okay, and you can also find out what is the other parts. I mean this part I believe you will be able to understand. The input voltage to the first stage, this voltage if I call it V in. So this is not exactly equal to Vs. This is your Vs. This voltage is the Vs. This is not exactly equal to Vs. Why? Because you have, if you apply KVL over there, so that voltage which is being developed over there by this particular back network, so back network receives a voltage equal to V naught, that is equal to VO2. VO is equal to VO2, the output voltage. And by virtue of this voltage division, it develops some feedback voltage over there. So what is the relation between VO and VF? You know, this VO and VF, how are they related? This is nothing but, VF is nothing but RE1 by RF plus RE1 times VO. That is the feedback voltage developed over here, and that voltage plus this input voltage, these 2 voltage is equal to your Vs. If I simply neglect this voltage drop across Rs. Okay, there will be some loss across Rs, but that you can safely neglect because this Rs is very small, so you can safely neglect that voltage drop. So otherwise, this V in voltage, this Vs voltage is equal to this V in voltage plus Vf voltage, or in other words, this V in voltage is equal to Vs voltage minus Vf voltage. So it's a negative feedback. V in is equal to Vs minus Vf. It's negative feedback. And how this Vf related to V naught? Vf is equal to RE1 by RF plus RE1 times V naught. Okay. What is the voltage gain with feedback, as you know, AVF, AV by 1 plus AVB. So AV by 1 plus AVB, and typically AV is large. Typically AV without any feedback, the gain is typically large with respect to B at least. So if it is large, then if you just divide this numerator and denominator by AV, then what you get? You get 1 there and then 1 by AV plus B. So 1 by AV will become 0. So 1 by B. So ultimately what is B? B is given by RE1 by RF plus RE1. So what is 1 by B? RF plus RE1 by RE1. So therefore ultimately the gain is given by 1 plus RF by RE1. Mark this particular value right at this particular point. 1 plus RF by something. 1 plus RF by something. You will once again encounter this value many times while you study the analog integrated circuit in the next semester, which involves op-amp. There you have one kind of gain which is known as the non-inverting voltage gain. That non-inverting voltage gain, the expression is given by 1 plus RF by something. 1 plus RF by R1. Non-inverting voltage gain. 1 plus RF by R1. That means even if this open circuit voltage, if for example you don't have sufficient knowledge about op-amp, and I don't want to discuss this over here because that will be discussed in the next semester. For the op-amp, for operational amplifier, the open loop voltage gain is very large, in the order of 10 to the power 4, 10 to the power 5. But ultimately, if I consider the closed loop voltage gain, this closed loop voltage gain is no longer dependent on that particular value, 10 to the 4, 10 to the 5. It depends on the feedback element. Once you connect the feedback in a non-inverting mode, then ultimately the gain with feedback becomes AV by 1 plus AVB. If I don't have any B, if I don't have any back network, then B is essentially 0. Then what is that AVF? Then AVF is equal to AV. But once you have some non-zero B over there, some feedback element present over there, then ultimately the gain with feedback becomes AV by 1 plus AVB. And if AV is very large, typically 5, then that can be approximated to 1 by B, that is equal to, in this particular case, 1 plus RF by RE. That means your gain now becomes very much stable. It's a function of resistances only.
So negative feedback is virtual sort.
So I'm not going to the details of that particular thing, but at this particular point, I would like to emphasize that, remember that expression of voltage gain, 1 plus RF by some resistor, 1 plus RF by R1. You will encounter this particular expression for the gain many times in the next semester while you study this analog integrated circuit. Okay. Okay, fine. So now only one feedback element, feedback topology is left. That is the current-shunt kind of thing. So for current-shunt, what has to be done? What change I have to perform over there for current-shunt? Can you tell me? Although I have shown you the what change I have to incorporate there for current-shunt?
The resistance to a basic.
For current-shunt, how can I collect the signal? How can I collect the signal?
Loop break code. Current series mixing.
No, I have to series mixing. No, it's not series mixing. It's a current-shunt. Shunt mixing. So current-shunt. That means I have to accept the current. I have to accept the current. So can it be connected to the collector terminal? Possibly no. You have to connect it at the emitter terminal. You have to connect it at the emitter terminal of the second stage, so that the current, a portion of the current, is fed back to the back network. Portion of the output current. And since it's a current shunt, so how to feed the signal in the feed network in the main network? Parallel means I have to feed it back not at the emitter but at the base. Not at the emitter but at the base. Now you may argue that whether this is a negative feedback or not. You may argue whether it's a negative feedback. So what I am saying, for your so for your current shunt kind of feedback, I cannot take the output from this terminal. I cannot take. What I have to do is that I have to take the output from this terminal only. from this terminal, and where I have to fit, I need to fit back at the base, right? Once again, argue. So I'm just once again showing you the variation of these voltages over there. So whenever this voltage or the base current for the stage 1, when it increases, you can expect more current at this particular stage collector, right? Or in other words, you can say, if this voltage goes positive, this voltage goes negative, right? Now, the stage 1 output is basically coupled to the stage 2 input. In the small signal models, they are basically shorted. So when this goes positive, this goes negative. Okay. Now, at this particular moment, I am not interested in observing this output voltage, because I have not taken the connection from this point. Rather, I have taken the connection from here, emitter terminal. So when this goes positive, input voltage over there, this goes negative. And from here to here, you have basically short. That means this base 1, base 2 of the second BJT, it experiences some negative excursion when the input excursion is positive. And this base 2 to emitter 2, there is basically a 0.7 volt drop. So when this goes negative, this also goes negative. Okay, when this goes negative, this emitter terminal also goes negative. It's not the collector terminal, it's emitter terminal. Base to emitter, you have only 0.7 volt drop. You have basically PN junction diode over there. Simple PN junction. So therefore, when this goes positive, base 1 goes positive. So I can write it over there. When base 1 voltage increases, that means the collector 1 voltage drops. That means base 2 drops, because C1 and B2, they are connected, shorted. If base 2 drops, that means emitter 2 also drops. And then this emitter 2 through emitter 2, you connect some feedback resistance to base 1. That means when E2 drops, that means the corresponding effect will drive the B1 to drop. So here B1 increases, the cause is B1 to increase, and the effect is B1 to reduce. So effectively, it will give you the notion of a negative. So now let's directly move into the circuit. Only one change we have made. Only one change we have made. This time, I don't want to have any local feedback at the first stage. So that's why, because that part is not our business over here this time. So that's why we have used some bypass capacitor, so that no local voltage series feedback present over there. No series feedback present over there, right? At this particular time or point.
So, extras capacitor.
I'm coming to that. So if you just compare this one, if you compare this particular amplifier with this one, here we have bypass this capacitor. Here we have used this particular bypass capacitor C2, so that no local feedback present over there. But this time I don't want to have a local feedback in the first stage. So that's why we have used this CE1, this in parallel to RE1. So no local feedback is present over there. No local series feedback is present over there. Okay. Next comes, obviously I can't have any bypass capacitor in the second stage, because if I have some bypass capacitor over there, that means this is basically shorted. You need to have some signal variation at this particular terminal. So that's why you have to eliminate that C2 that was there last time. Okay, C2. The C2 was there from here to here, so that no local feedback was there. But here I don't want to have this, because I would like to have this variation at the emitter 2 terminal. So that's why this bypass capacitor is eliminated. I am imposing some feedback from this particular terminal itself. So it is connected back through some resistance RF back to base 1. Now the question is that why this capacitor CF is present? That is your question, why CF was there? Now what we are doing basically, as far as the small signal behavior is concerned, it's okay, perfectly okay. Right, but what we are doing, we are also connecting this output E2, this output voltage back to base 1. So when it comes to the DC analysis, it may affect the biasing stability of this particular first stage. Right. In order to get rid of that, we have used some capacitor over there CF between the E2 and the B1, so that even if you have this feedback connection from here to here, this will not seriously hamper any DC operating point. Only the small signal behavior, the small signal feedback will be present from E2 to B1, but the corresponding bias point is kept at its nominal value. Okay, so this is known as the current-shunt feedback amplifier. So in this particular case, the biasing is relatively easy. We have used only RB1 and RB2. You can also go for this parallel combination, doesn't matter. You can also go for this voltage divider bias, doesn't matter. Right? Now let's move to the small signal model. Let's move to the small signal model. This part is relatively easy. R5 1, GM1, V5 1, R01 for the first BJT, and R5 2, GM2, V5 2, R02 for the second BJT. Okay. What else? We have RB1. We have RB1 connected between base 1 and AC ground. So base 1 to AC ground, we should have some RB1 present over there. What about E1? Is it an AC ground? E1? Yes, it is, because you have this bypass capacitor present. So I can safely connect this RB1 between base 1 and emitter 1. That means RB1 is in parallel with R5 1. You have GM1, V5 1 between C1 and E1. You have RO1 between C1 and E1. You have RC1 between C1 and AC ground. That means between C1 and E1, because E1 is at AC ground. RC1. You have RB2 between B2 and AC ground. That means between B2 and E1, because E1 is at AC ground. This is essentially at, remember, this is essentially at this terminal, is essentially at AC ground. AC ground. This is not hard ground, this is AC ground.
Constant voltage.
Constant voltage. Okay. What else? Okay, R5 2, R5 2, GM2, V5 2, RO2 have already done. What else? RE2. How is it connected? RE2, it's connected between emitter 2 and DC ground, or emitter 2 and ground. So this is an emitter 2 terminal through ground. RE2, this is your ground line, this lower one, this is the ground line. Okay. What about RC2? It is connected between collector 2 and DC ground. This is collector 2 terminal. This is AC ground terminal. These two are connected. Okay. What else? RF. RF. Now it's a shunt mixing. Since it's a shunt mixing, that means we are mixing the current. So it is easy to analyze the input side as a current amplifier. So instead of having VS-RS combination, let's have some IS-RS combination. you know that this voltage source, because of this source transformation, you can have this voltage series. You can have this voltage source can be represented by means of some current source. If you have Vs, Rs in series, Vs and Rs is in series with Vs, that is nothing but Is in parallel with Rs, where Is value is equal to Vs upon Rs. So by virtue of this source transformation, what I can have, I can represent this Vs by means of some current source, Is, and in parallel with Is, you must be having Rs. How Is is connected? Is is connected between V1 and AC ground, V1 and hard ground. V1 and hard ground, Is is connected. So Rs, this is also connected between V1 and hard ground. So this Is and Rs, both of them are connected between V1 and hard ground. Remember, this RB1 was connected between base 1 and AC ground, right? So therefore, I can combine this Rs and RB1 together. I can combine them together, Rs and RB1, something like this. What is left? Rs. How is it connected? Between E2 and V1. Rs. E2 and V1. Between E2 and V1. So this is the E2 terminal. This is E2 terminal, and V1 over here. Last bench note of between E2 and V1, this RF is connected. Okay, E2 and V1. How to connect? Like this. How to connect this ground line over there? Hard ground. This is hard ground, no? That means whenever you connect this terminal to hard ground, so over there, AC ground, if you have some AC ground in this small signal module, E1 is at AC ground, and hard ground, if you have hard ground, that is obviously AC ground. Hard ground is AC ground, obviously, right? So that's why these two are also connected. Now you take a look at this particular feedback stage. How do you sample the signal? Have you broken the loop? Yes or no? Have you broken the loop input side? From output side, if I observe sampling. Yes. So you have broken the loop here. So it's basically a current sampling. How do you mix? You mix in parallel path. That means it's a shunt mixing. So it's a current shunt feedback amplifier, and it involves a negative feedback. You have to understand that okay, it's a current shunt, but whether it's negative or positive feedback, it's a negative feedback. Why? Because base 1 to collector 1, B1 to C1, there is a 1 phase difference. C1 to B2, no phase difference because they are connected. AC wise they are connected. B2 to E2, there is only 0.7 volt drop. So therefore, E2 to B1, you have 180 degree phase difference. Right. So I can simply have a resistance between E2 and B1 by virtue of this particular thing. Right. So current shunt and voltage series, these two type of feedback topology using a single stage common emitter amplifier. But last day I have told you that you have, apart from this common emitter amplifier, you have other two types of amplifier. One is common base, another one is common collector. Right, common base and common collector. And therefore, you can represent both of these last two types of amplifiers, feedback amplifiers, current shunt and voltage series, using either common base or common collector. Is it clear? So let me just show you the final expression. This one, the expression for this current gain this time here, because of the current gain, because input side you have current, output side you have current, right? Input side you have current, output side you have current. Because current shunt means what? Current is the signal that you are sampling. Shunt path you are mixing, that means you are mixing the current as well. So you are getting the current, you are mixing the current. So current versus current. So current amplification. So 1 plus RF by RE2. For very large voltage gain, for very large current, if AI is very large, in that case AI is upon 1 plus AIB. That gives rise to 1 plus RF by RE2. So remember that expression, 1 plus RF by something. That is very important. That, I mean, these two things, one is this minus RC by RE, you remember na? Minus RC by RE. That expression, minus RC upon RE. So, these two types of feedback, I mean these two types of expressions, you have to remember while you study this op amp in the next semester. One is the non-inverting voltage gain, second one is inverting voltage. For the inverting voltage gain, what is the expression? Minus RF by R1. And for non-inverting case, what is the voltage gain? 1 plus RF by R1, something like that. Right? Okay, so fine. So we have discussed everything related to feedback amplifier using common emitter stage, C stage. Now it comes to the common phase or common collector. Now if I go for voltage series kind of thing, voltage series, right? Then what should be the type of the amplifier? Is it a common phase or common collector? Voltage series. Last time I told you. Voltage series. Voltage series. That means you are sampling the voltage. You are mixing it as a voltage. Voltage. Right. That means input side you are mixing it in series. So input resistance will be larger. And the output side you are sampling as a voltage. That means you have connected something in parallel. So output resistance will drop. So input resistance large, output resistance small. That is the characteristics of a common collector amplifier, right? So using a single stage common collector, hopefully I'll be able to have a common to have some voltage series kind of feedback amplifier. Let's have a look. This is a typical common collector amplifier. Typical common collector amplifier, you know, right? Collector is connected to VCC. You have RB, that resistance was there for biasing and all. And this input side you have this signal VS with some associated source resistance RS, coupling capacitor present over there. And RE is basically the output resistance between the emitter and the signal, because the output is sensed at the emitter terminal for the common collector amplifier, right? Now, if I ask you to check whether this particular, I mean, you can always draw the small signal model for this. You have drawn it previously many times. Now, this time you have to draw the small signal model in such a way that it looks like a feedback amplifier. It must be having that resemblance. This feed network, this back network, and that connection. That is important. You don't get this anywhere in any book. You don't get it. You don't get it. Now, the thing is that you have to explain, you have to justify that whether this common collector stage can be used as a voltage series feedback amplifier or not. Typically, ultimately, since it's a common collector, so the voltage gain will be ultimately equal to 1, close to unity. Okay, that means what? Typically, you know that AV upon 1 plus AVB or A by 1 plus AB. That is the notion A by 1 plus AB. So typically, this B is essentially equal to unity, so that A by 1 plus A. So ultimately, it's close to 1 unity. But still, you have to represent that one in terms of a feed and back communication. Let's have a look. I think you are not overloaded. I hope so. I hope so that you are not overloaded. Okay. Pause for a minute. Well, I have drawn this upside down. This is the base terminal. Typically, we draw emitter downwards, collector upwards, but this time it's a common collector. So collector. So typically the reference voltage is normally kept at the lower terminal, right? So since here we have the collector terminal as the common terminal, which is equivalent to AC ground. So therefore, let's consider this is my collector terminal. Let's consider, right? Okay. What we have, first of all, between base and emitter, you must be having some R pi. Between base and emitter, you must be having some R pi. You must be having some GM pi between collector and emitter, and you should have some R naught between collector and emitter. So for the time being, let's forget about this R pi. Let's identify this is my base terminal. So this has not been marked over there anyway. So let me mark. This is my base terminal. This is my emitter terminal. This is my collector terminal. Typical what I draw. Base, collector, base here, collector here, emitter there. This time base here, emitter here, collector here. So I cannot. So this is not your R pi. Remember, since collector is at AC ground, and we have RB present between the base and the collector, base and the VCC. That means this RB is present between the base and the AC ground. So I can draw this RB between base and collector. Done. Between collector and emitter, you have this GM pi, voltage dependent current source, and take a look at the direction. The direction of the current source from collector terminal to the emitter terminal. That's upwards, not downwards.
So collector is at AC ground, right?
Collector is at AC ground. Let's assume that this is AC ground. Let's assume. We'll prove. Between collector and emitter, you have some RO. Right? This one. Collector and emitter. Done. Only one is left. Or rather, two is left. Two are left. One is this RE, and second one is your R pi. Right? How is RE connected? RE is connected between emitter and AC ground or DC ground. DC ground, if we consider, okay, this is this hard ground, and hard ground is equivalent to AC ground. DC ground is equivalent to AC ground. So this is connected between E and ground. So this is your emitter terminal. This is your, let's assume this is my ground terminal. This one is the ground terminal. So between ground and emitter, you have this RD, this one, right? Is it okay? You may argue that আমি তো এখানেই connect করতে পারতাম. You may argue. Yes, in order to have this particular structure, what I have done, I have connected like this. I can directly connect from here too. So RE is there. What else? That R pi. How is it connected? Between base and emitter. So this is your emitter terminal. This is your base terminal. Now you may argue that I can always connect like this. I can connect, no, but I am connecting in that fashion. Like this. Done? And now since this is your ground terminal and this is your collector terminal, collector is at AC ground, so this should be connected. This should be shorted. Okay? This should be connected. And obviously VS is connected between base and ground. That's quite obvious. Right? Now you tell me, how do you sample the signal? Rishi Roy, how the signal is sampled here? How the signal is sampled? How the signal is sampled? Okay, voltage sampling, true. Voltage sampling. How have you sampled? You have sampled in parallel path. So it's a voltage sampling. So you just check, these are the two terminals which are connected to the input of the back network from the output of the feed network. How are they connected? Have you broken the loop? No. Parallel connection. So it's a voltage sampling. How are you mixing? Have you broken the loop? Yes. Series mixing. Right? Voltage sampling, series mixing. So it's a voltage series kind of feedback amplifier. What is your V value? I mean, what is the feedback factor? VF upon V naught. What is VF upon V naught? That will be interesting. This is your V naught voltage. This voltage is a V naught. This voltage is a V naught. And this is the feedback voltage here. Right? So they are same. They are equal. V naught and VF, they are equal. And what is your input voltage? This input voltage is basically Vs, that is equal to, you can have Vs is equal to V pi plus Vf, or you can write V pi is equal to Vs minus Vf. So it's a negative feedback. It's a negative feedback, right? So the thing is that here the feedback factor V is equal to 1 unit. V is equal to 1. Typically V is less than 1. But this time V is equal to 1. Because ultimately your circuit is a common collector. So overall voltage gain cannot be greater than 1. It cannot have 1 plus Rf by Re, something like that. Right? Ultimately it's a common collector. But it must be having that particular form. So what was the form? The form was A by 1 plus AB. So AB by 1 plus ABB, and here AB is equal to, AB can be large, but B is equal to unit. The feedback factor is equal to unit, because this V0 and VF, they are the same voltage, right? So ultimately your AVF, voltage gain with feedback, is equal to AV by 1 plus AV, and for very large AV, that is almost close to 1, and that satisfies your intuition that for common collector amplifier, the voltage gain is close to 1 but less than 1. But it is having that particular form, AV by 1 plus AVB.
Less than 1?
Less than 1. Close to 1 but less than 1. Right. So common collector amplifier can be regarded as a voltage series feedback amplifier. So only one is left. Only one, that is the current series. And this, no, voltage we have discussed already. So current shunt is left. Current shunt is left using common base. This is a typical common base amplifier. Typical common base amplifier, input is applied at the emitter terminal, output is sensed at the collector terminal. Input is at the emitter terminal, output is sensed at the collector terminal, base is ground. So we have used some capacitor over there, so that even if some small signal is generated, that is having the corresponding ground ones. So you have drawn the small signal model for common base stage many times. Now this time you have to identify this as a current shunt feedback amplifier. Right. Now take a look at once again. Since it's a current shunt kind of thing, therefore current to current. So input side, I would like to have, I prefer some current source, not a voltage source. Anyway, so base is at the bottom over there. We have emitter terminal there, you have collector terminal over there. Between base to emitter, you have this R pi. Typically, between base to emitter, you have R pi. And apart from that, what else? Base is at AC ground. Base is at AC ground. And remember, this RB is also there between base and the AC ground, VCC. So therefore, I can have this RB between base and emitter. So RB and R pi, both of them are between base and emitter. R pi is always between base and emitter, and RB is there between base and the AC ground, and here emitter is at AC ground. So therefore, RB, R pi, both of them are between emitter and the base. Between collector to emitter, you have this GM V pi. This is the direction of the current from collector side towards the emitter side. Where V pi is that voltage, base to emitter, that voltage is the V pi voltage.
So emitter AC ground.
Base to base.
Base is AC ground. No, emitter is not at AC ground. Base is at AC ground. Base is at AC ground, and RB is there between base and the VCC. That means base.
Base and AC
ground.
Oh, so in that case, RB will not be there. Yes, so RB will not be there in that case. Yes, that is absent. That is not present. Yeah.
Into ground and move the other.
Yes, RB will not be there. Right. RB is not there. RB is not there. You only have R pi between emitter and base. Okay. Okay. What else? You have R naught between collector and emitter. This one R naught. You have GM V pi between collector and emitter. With this is the direction of the current from collector to emitter. What is V pi? V pi is this voltage plus minus. This is your V pi. Right. What else? I need to connect RE. How to connect RE? RE is there between emitter and the ground. Emitter and the ground. So this is the emitter terminal. So from emitter and ground. Ground is base. So I can connect like this. Right? What about RC? RC is there between collector and the AC ground. This is the collector terminal, this is AC ground. Suppose this is my ground terminal. Right? RC is connected like this. Now if you observe, this is the output current IO. Have you taken the connection in shunt path? Have you broken the loop or you have connected in parallel? You have broken the loop. So it's a current sampling. Right? And how are you feeding?
Not breaking all.
In parallel. In shunt path you have connected. You have fed. So it's a current shunt feedback. Current shunt feedback. Right? And here what do you understand? This IF, this feedback current, last time we have seen that this feedback voltage is equal to the output voltage. TF is almost equal to V naught. So here you find this particular thing. Here you find that this current IO, this current is actually moving through this. No? This current. So IF is equal to IO. So V value is equal to 1. IF is equal to IO. So V value is equal to 1. And what is your IS? IS is equal to actual input current plus IF. So I can write I in is equal to, so if I apply KCL at this particular node at the emitter terminal, what I find, I in is equal to IS minus IF. This current is IS, this is the current. Let me have some different color. This current is IS, this current is I in, and this current is IF. Okay, so therefore if I apply KCL at this particular node, what I get? This input current plus feedback current is equal to the source current. So IS is equal to IF plus I in, or I in is equal to IS minus IF. So it's a negative feedback. Negative feedback, right? And what is the gain with feedback? It's a common base amplifier. For common base amplifier, what is your input current? Input current is the emitter current. What is the output current? That is the collector current. So as you have seen last time, for a voltage series kind of feedback, you have seen the voltage gain is equal to close to unity, less than unity. And here, for the common base stage, what you have, input current is emitter current, output current is the collector current. Right? So their ratio, collector by emitter, that ratio is basically IC upon IE, that is equal to alpha. That is beta by 1 plus beta, which is always less than unity. So here you find AI, so typically what happens, AIF is equal to AI upon 1 plus AIB, and here B is equal to unity. So AI upon 1 plus AI, right? And what is that AI? That AI is without any feedback. What is that gain? That gain is a beta. Beta. So beta upon 1 plus beta. Right. So it's a manifestation of a current shunt feedback amplifier. using a common base stage, single stage common base amplifier. So we have developed this current shunt amplifier and the voltage series and feedback amplifier using the common base and the common collector stage respectively. Single stage, common base, single stage, common collector. Apart from that, you can also have multi-stage common emitter amplifier to develop all such 4 types of feedback. For current shunt and voltage series, you require 2 stages, and for voltage series and for voltage shunt and current series, you require only 1 stage of common emitter amplifier. So with this, we have come to the end of this feedback amplifier unit, and in the next day, we will discuss the oscillator circuit in detail.